The Wyoming wind cut through everything that first winter of 1858. Samuel Crawford learned that the hard way when his water bucket froze solid just 4 feet from his roaring fireplace and frost formed on the inside walls of his brand new cabin. He had built it exactly like every other settler in the territory was told to build: 8 foot ceilings for proper airflow, raised foundation, tight log construction, standard and proven. By February, he had burned through twice the firewood his neighbors predicted, and still the cold seeped through every corner. Across the high plains, homesteaders were losing the same battle in cabins built by the book and failing by the season. The next spring, Crawford quietly lowered his ceiling to just 6 feet, a move that earned him mockery from every settler within 20 miles. While their standard cabins continued to lose heat and devour firewood, Crawford's odd little cabin held 15 degrees warmer through the following winter with half the fuel. What did this New England carpenter understand about trapping heat that every frontier building guide had missed? Samuel Crawford had spent 12 years building homes in the granite-hard winters of New Hampshire before the promise of free land drew him west to Wyoming territory. He knew cold. He had framed houses where January temperatures dropped to 20 below zero, where poorly built homes meant death, not just discomfort. When he filed his homestead claim on 160 acres north of Fort Laramie in the spring of 1857, he carried with him the accumulated knowledge of a dozen brutal New England winters and the skills to build shelter that could withstand them. The standard frontier cabin design made perfect sense on paper. Military construction manuals distributed by the territorial government recommended 8 to 9 foot ceiling heights to maximize interior air volume and prevent the cramped, stifling conditions that drove men to madness during long winter confinements. Land company guides echoed this advice, explaining that higher ceilings allowed proper air circulation and reduced the oppressive feeling that came with months of indoor living. Even the Methodist circuit riders who passed through the territory praised the psychological benefits of spacious interiors, claiming they prevented the cabin fever that had claimed settlers' sanity across the frontier. Crawford followed every recommendation to the letter. He raised his foundation 18 inches off the ground using fieldstone, exactly as the territorial surveyor had advised, to prevent ground moisture from rotting the sill logs. He chinked every gap between his logs with a careful mixture of mud and grass, creating walls so tight that not even the thinnest knife blade could slide between them. His fireplace, built from local sandstone, drew perfectly and threw heat exactly as it should. By every measure, his cabin represented frontier construction at its finest. But the cold had different rules at 4,000 feet above sea level. Crawford watched his carefully banked coals die to ash every night, despite loading the firebox with enough split pine to burn until dawn. He woke each morning to ice crystals covering his water bucket, even when he positioned it directly in front of the hearth. Worse, the interior walls themselves became cold sinks, drawing heat from the room faster than his fire could replace it. By Christmas of 1858, he was splitting and hauling 4 cords of wood every 2 weeks, a pace that would exhaust his timber reserves before spring. His nearest neighbor, Thomas Brennan, faced identical problems in a cabin built using the same proven methods. Brennan, a former railroad foreman from Illinois, had constructed his home with military precision, following territorial guidelines down to the inch. Yet his family spent their first Wyoming winter wrapped in buffalo robes around a fire that consumed wood faster than 2 men could cut it. 3 miles south, the Kowalski family huddled in a cabin with 9-foot ceilings that stayed so cold their stored potatoes froze solid, despite being kept inside near the stove. Crawford began to question what everyone assumed was correct. His New England experience whispered that something fundamental was wrong with the accepted wisdom. In New Hampshire, the old-timers built low-ceilinged cottages that held heat like stone ovens. He remembered visiting a trapper's cabin in the White Mountains with a ceiling so low he had to duck when walking across the room, yet the interior stayed warm enough for a man to work in his shirt sleeves while snow piled 3 feet against the door. The physics made sense when he thought it through. Heat rises. In a cabin with an 8-foot ceiling, the warmest air gathered uselessly near the roof logs while the living space below remained cold. All that extra air volume that was supposed to provide comfort simply gave the heat more places to hide beyond the reach of human bodies. Every cubic foot of space above 6 feet represented wasted fuel and wasted warmth. Crawford spent the spring of 1859 planning his modification. Using his carpenter's knowledge, he calculated that lowering his ceiling from 8 feet to 6 feet would reduce his interior air volume by 25%. Less air to heat meant less fuel required to maintain temperature. The mathematics were elementary, but the social cost would be significant. When he began removing his roof in late April and announced his intention to rebuild with a 6-foot ceiling, the reaction was swift and merciless. Brennan declared the plan foolish, insisting that a grown man needed headroom to maintain his dignity and sanity. The territorial land agent who rode through in May examined Crawford's work and warned him that low ceilings would make the cabin feel like a tomb, driving him to despair before the first snowfall. Even the local preacher expressed concern, suggesting that God intended man to live with space above his head, not cramped like an animal in a burrow. The mockery followed Crawford through every stage of construction. When he carefully lowered each roof beam and reset them 24 inches below their original position, neighbors gathered to watch what they considered a demonstration of frontier folly. Brennan brought visitors from Fort Laramie specifically to see Crawford's mouse hole, as they called it. The Kowalski children were forbidden from playing inside the modified cabin because their parents feared the low ceiling would stunt their growth. But Crawford possessed something his critics lacked: the certainty that came from watching the standard method fail repeatedly and catastrophically. He had calculated fuel consumption, measured interior temperatures, and observed the precise ways that heat moved through frontier buildings. While his neighbors relied on accepted wisdom and collective assumptions, he trusted his carpenter's understanding of how buildings actually functioned in harsh conditions. As autumn approached, Crawford prepared for his second Wyoming winter with quiet confidence. His modified cabin looked strange from the outside, its roofline lower and more compact than any other structure in the territory. Inside, the reduced ceiling created an intimate space that felt solid and purposeful rather than cramped. He had created something new on the frontier, a cabin designed not for appearances or social expectations, but for the precise demands of high-altitude cold. The real test would come with the first blizzard. The winter of 1859 brought vindication for Crawford's ceiling modification, but it also revealed a problem he had not anticipated. While his 6-foot ceiling trapped heat effectively in the upper portion of the cabin, his floors remained brutally cold. Each morning, ice formed in the corners where the wooden planks met the foundation stones, and his feet went numb within minutes of stepping out of bed. The raised foundation that territorial guidelines demanded for moisture protection had created a crawl space that acted like a wind tunnel, channeling frigid air directly beneath his living space. Crawford measured the temperature differential with a mercury thermometer borrowed from the fort's doctor. While the air near his ceiling held steady at 68 degrees Fahrenheit during the day, the floor temperature dropped to 34 degrees, just barely above freezing. His neighbors faced identical conditions, but their higher ceilings masked the problem by creating such overall cold that the floor temperature seemed merely one more discomfort among many. The solution came from an unexpected source. In late February of 1860, during a brief warming spell, Crawford encountered an Ojibwe hunter named McGeezy tracking elk through his timber claim. The man had traveled south from the Great Lakes region, where his people had survived winters far more severe than Wyoming's high plains. When McGeezy accepted Crawford's invitation to shelter from an approaching storm, he examined the cabin's construction with the eye of someone who understood cold as a mortal enemy. McGeezy spoke adequate English, learned during trading expeditions to Detroit, and his observations cut straight to the fundamental flaw in frontier building practices. The Ojibwe built their winter lodges partially underground, he explained, using the earth itself as insulation. At depths below the frost line, soil temperature remained constant year-round, typically between 45 and 50 degrees Fahrenheit, even when surface temperatures dropped far below zero. By embedding structures into the earth, rather than elevating them above it, his people harnessed this stable ground temperature to moderate their indoor climate. The concept challenged everything Crawford had learned about foundation construction. Standard practice dictated raising buildings above ground level to prevent moisture damage and wood rot. Territorial guides warned specifically against ground contact, citing ruined cabins and collapsed structures throughout the frontier. But McGeezy's explanation revealed the flaw in this reasoning. Elevated foundations prevented moisture problems, but created thermal problems that consumed far more resources than occasional wood replacement would cost. Crawford spent the remainder of that winter studying the principle. During March, when frost began leaving the ground, he dug test holes at various depths around his property. At 18 inches below surface level, his thermometer registered 42 degrees Fahrenheit even when morning air temperatures hit 15 below zero. The Earth maintained its temperature with mathematical consistency, acting as a massive thermal battery that absorbed heat during summer and released it slowly throughout winter. The practical application required careful engineering. Crawford could not simply bury his existing cabin, but he could modify his foundation system to capture ground warmth rather than fighting it. Using techniques developed during his New Hampshire construction days, he planned a foundation trench that would lower his floor level while protecting the log sills from direct earth contact. Beginning in April of 1860, Crawford excavated a trench 18 inches deep around the entire perimeter of his cabin. He lined this trench with carefully fitted field stones, creating a thermal bridge between the stable ground temperature and his interior space. The log sills rested on these stone walls, protected from moisture, but positioned low enough that his wooden floor planks lay just 6 inches above the surrounding soil level. The most critical element was drainage. Crawford installed a French drain system along the uphill side of his cabin, using techniques learned from New Hampshire cellar construction. He laid a bed of graded gravel beneath his stone foundation walls and created channels that directed water away from the structure. This prevented the moisture problems that territorial guides warned about while maintaining the thermal connection that standard raised foundations severed. The work required precision that went far beyond typical frontier construction standards. Each foundation stone needed individual fitting to create thermal continuity without gaps that would allow air infiltration. Crawford spent 6 weeks on foundation work that most settlers completed in 3 days, but his carpenter's training had taught him that foundations determined everything that followed. When Crawford reconstructed his floor during the summer of 1860, he incorporated another principle McGeezy had shared. Instead of leaving an airspace beneath his floorboards, he packed the area with a mixture of clay soil, sand, and chopped grass that created a thermal mass extending directly from the earth into his living space. This material absorbed ground warmth during the day and radiated it upward through the floorboards during cold nights. The Kowalski family, struggling through their second winter in a standard raised foundation cabin, watched Crawford's construction project with skeptical interest. Thomas Brennan dismissed the modification as unnecessary labor, insisting that proper firewood management could solve any heating problem. The territorial land agent, returning for his annual survey, noted Crawford's foundation work in his official report as irregular construction not conforming to standard territorial building practices. But Crawford possessed temperature measurements that proved his approach. After completing the thermal foundation system in late August, he began collecting systematic data using his mercury thermometer. Morning floor temperatures in his modified cabin registered 48 degrees Fahrenheit when outside air measured 20 below zero. His neighbors' elevated cabins showed floor temperatures of 32 degrees under identical conditions, a 16-degree differential that translated directly into fuel consumption. The broader implications extended beyond personal comfort. Crawford calculated that maintaining his floor temperature required approximately 30% less firewood than heating the same space from a 32-degree starting point. Over a full winter, this represented a savings of nearly 2 cords of split wood, enough fuel to extend his timber reserves by 6 weeks, or trade for essential supplies at Fort Laramie. As autumn approached, Crawford prepared to test his complete thermal system. The low ceiling that trapped warm air in the living space, combined with the earth-coupled foundation that eliminated cold floors. He had created something unprecedented on the Wyoming frontier, a cabin designed around thermal principles, rather than conventional appearance or standard practice. The approaching winter would reveal whether his systematic approach to heat management could achieve the kind of efficiency that would change how settlers built homes across the High Plains. Crawford's success with his thermal foundation system revealed another critical weakness in frontier construction. During October of 1860, as nighttime temperatures began dropping toward freezing, he discovered that heat was escaping through his log walls faster than his improved floor and ceiling could compensate. Using his thermometer, he measured the interior surface temperature of his chinked log walls during a cold snap and found them registering 41 degrees Fahrenheit while his room air held steady at 65 degrees. The logs themselves were acting as massive heat sinks, conducting warmth directly from his interior to the outside air. Standard frontier wall construction relied entirely on the thermal mass of thick logs to provide insulation, but Crawford's measurements proved this assumption false. Pine logs, even when seasoned and tightly fitted, conducted heat with remarkable efficiency. His exterior walls, built from logs averaging 8 inches in diameter, showed no significant temperature difference between their interior and exterior surfaces during cold weather. Every British thermal unit his fireplace produced was bleeding through these thermal bridges directly into the Wyoming wind. The solution came through an encounter with Swedish immigrants who had established a small settlement 30 miles northeast of Fort Laramie. In November of 1860, Crawford traveled to their community to purchase iron hardware and encountered building techniques that challenged everything he thought he knew about wall construction. The Swedes had arrived in Wyoming with knowledge earned through centuries of surviving Scandinavian winters that regularly reached 40 degrees below zero. Lars Eriksson, a stone mason from Gothenburg, invited Crawford to examine his family's cabin, which had kept them comfortable through 2 Wyoming winters using significantly less firewood than their neighbors required. The structure appeared unremarkable from the outside, but the interior walls revealed a sophisticated insulation system that Eriksson had adapted from traditional Swedish construction methods. Eriksson had lined his interior log walls with a carefully engineered barrier consisting of 3 distinct layers. The first layer, applied directly against the logs, consisted of dried bog moss harvested from creek beds during late summer. This moss, when properly prepared and installed, created thousands of tiny air pockets that interrupted heat conduction through the wood. Over the moss, Eriksson had applied a mixture of clay-rich soil, chopped grass, and animal hair that formed a continuous thermal barrier approximately 2 inches thick when dried. The final layer represented the most innovative element of the system. Eriksson had obtained elk hides from Oglala hunters and processed them using traditional Swedish leather-working techniques that left the hide supple but airtight. These hides, stretched and secured over wooden battens, created an interior wall surface that sealed the insulation system while providing additional thermal resistance. Crawford examined Eriksson's thermometer readings with fascination. During a week when outside temperatures averaged 15 degrees below zero, the Swedish cabin's interior walls maintained surface temperatures of 58 degrees Fahrenheit while the room air stayed at 70 degrees. This represented a thermal performance Crawford had never seen in frontier construction. The practical implementation required materials readily available on the Wyoming frontier, but demanded techniques that went far beyond standard homesteading skills. Crawford began gathering supplies in December, collecting moss from unfrozen creek margins, and trading with local hunters for elk and deer hides. The clay-rich soil component came from a deposit he located 2 miles south of his claim, where seasonal flooding had created a natural mixture of fine clay and organic matter. Processing the materials required precise timing and careful technique. Crawford learned to prepare the bog moss by drying it in his cabin during January, then grinding it to a consistent texture that would pack evenly against the log surfaces. The clay mixture demanded exact proportions: 3 parts clay soil, 2 parts chopped prairie grass, and 1 part animal hair obtained from buffalo hides processed at Fort Laramie. The most challenging element was preparing the elk hides for interior wall application. Using techniques Eriksson had demonstrated, Crawford scraped each hide to uniform thickness, then treated them with a solution of oak bark extract that prevented cracking while maintaining flexibility. The hides needed to remain workable during installation but cure to an airtight finish that would last through repeated heating and cooling cycles. Crawford began installing his wall insulation system in February of 1861, working on one wall section at a time to maintain livable conditions in his cabin. He applied the moss layer first, pressing it firmly into every irregularity in the log surface to eliminate air gaps that would create thermal bridges. The clay mixture went on next, troweled to a consistent 2-inch thickness, and scored with a wooden comb to create mechanical bonding with the final hide layer. Installing the elk hide covering required carpentry skills that few frontier settlers possessed. Crawford cut each hide to precise dimensions, then stretched it over a framework of thin wooden battens secured to the logs with hand-forged nails. The hides needed sufficient tension to remain flat against the insulation layer, but not so tight that they would crack when the cabin's wood expanded and contracted with temperature changes. Thomas Brennan, observing Crawford's wall modification project, declared it the work of a man who had clearly lost his mind to cabin fever. The territorial land agent, making his spring survey, noted that Crawford's interior modifications had created a cabin that no longer conformed to any recognizable frontier construction standard. Even some of the Swedish settlers questioned whether Crawford's adaptation of their techniques would work in a cabin not originally designed for such modifications. But Crawford's systematic approach yielded measurable results that silenced his critics. By March of 1861, his completed insulation system was maintaining interior wall surface temperatures averaging 12 degrees warmer than unmodified cabins under identical weather conditions. More significantly, his fuel consumption had dropped to less than 3/4 of what neighbors with standard log walls required to maintain comparable interior temperatures. The thermal performance translated into practical advantages that extended beyond simple comfort. Crawford's reduced firewood requirements meant he could maintain his timber reserves through extended cold snaps that forced neighbors to burn furniture and fence rails. His consistent interior temperatures prevented the freeze-thaw cycles that caused stored food to spoil in poorly heated cabins. Most importantly, Crawford had proven that systematic thermal engineering could overcome the limitations that territorial construction standards accepted as unavoidable facts of frontier life. His cabin now featured 3 integrated systems working together: a low ceiling that trapped warm air, an earth-coupled foundation that eliminated cold floors, and insulated walls that prevented heat loss through the building envelope. As spring arrived, Crawford possessed the most thermally efficient structure in Wyoming Territory, a cabin that had consumed 40% less firewood than standard construction, while maintaining superior comfort throughout the winter. Crawford's thermal improvements had created an unexpected consequence that became apparent during the spring thaw of 1861. His tightly sealed, heavily insulated cabin was trapping moisture along with heat, creating condensation problems that standard frontier construction had inadvertently avoided through its inherent air leakage. Water droplets formed on his interior walls each morning, and by April he detected the musty odor that indicated mold growth beginning behind his elk hide wall covering. The problem stemmed from basic physics that territorial building guides had never addressed. Human respiration, cooking, and the moisture content of burning wood produced approximately 2 gallons of water vapor daily inside a frontier cabin during winter. In standard leaky construction, this moisture escaped through gaps in the walls and roof before it could condense. Crawford's airtight insulation system prevented this natural ventilation, creating interior humidity levels that exceeded the capacity of heated air to hold moisture in suspension. Using a crude hygrometer constructed from human hair and wooden components, Crawford measured interior humidity levels that reached 80% during cold snaps when he kept his cabin sealed against outside air. These conditions created perfect breeding grounds for mold and presented serious health risks that could develop into respiratory ailments or worse. His thermal efficiency meant nothing if the indoor environment became uninhabitable. The solution required understanding airflow principles that went beyond simple heating and cooling. Crawford needed to create controlled ventilation that would remove moisture-laden air without sacrificing the thermal performance he had worked 2 years to achieve. Standard frontier cabins used crude ventilation holes covered with wooden shutters, but these created significant heat loss and provided no control over air circulation patterns. During a trading expedition to Fort Laramie in May of 1861, Crawford encountered James Mackenzie, a former Hudson Bay Company trader who had spent 15 years building and maintaining wilderness cabins across the Canadian Rockies. Mackenzie possessed knowledge of roof design principles that addressed moisture management in cold climates, techniques developed through necessity in regions where condensation problems could prove fatal during extended winter trapping seasons. Mackenzie explained that effective moisture control required understanding the stack effect, the natural tendency of warm air to rise and create air pressure differences that could drive ventilation. Standard frontier roofs, with their shallow pitches and sealed peak construction, actually fought against this natural air movement, trapping warm, humid air in the highest portion of the cabin where it would cool and condense against the roof boards. The key lay in roof geometry and controlled air outlets. Mackenzie had learned from Cree builders to construct roofs with steep pitches that encouraged rapid air movement, combined with ridge vents that allowed moisture-laden air to escape at the highest point where thermal buoyancy created the strongest upward flow. This system worked with natural physics rather than fighting against it. Crawford spent the summer of 1861 redesigning his roof structure using principles Mackenzie had shared. He increased his roof pitch from the standard 4-12 slope to a much steeper 8-12 configuration that created a more pronounced peak and encouraged stronger air circulation. This required rebuilding his entire roof framework using longer rafters and additional structural support, work that neighbors viewed as another example of Crawford's obsessive perfectionism. The most critical innovation was the ridge vent system. Crawford created a continuous opening along his roof peak by leaving a 4-inch gap between the upper edges of his roof boards on both sides. He covered this gap with a wooden ridge cap that overlapped the opening while allowing air to escape through carefully calculated gaps at regular intervals. The design prevented rain and snow from entering while maintaining constant airflow that would remove interior moisture. To control the intake of replacement air, Crawford installed adjustable vents near his foundation level on the cabin's windward side. These vents, constructed from hollowed sections of pine log fitted with sliding wooden covers, allowed him to regulate the volume of incoming fresh air based on weather conditions and interior humidity levels. During severe cold, he could restrict airflow to minimal levels. During milder weather, he could increase ventilation to rapidly reduce interior moisture. The system required precise balancing between heat retention and moisture control. Crawford installed a baffle system inside his ridge vent that directed escaping air away from his living space while preventing backdrafts during high wind conditions. He constructed these baffles from thin pine boards, arranged in a series of overlapping channels that created a tortuous path for air movement, slowing the flow enough to prevent excessive heat loss while maintaining consistent moisture removal. Testing the system during the autumn of 1861 revealed the complexity of managing both thermal and moisture dynamics simultaneously. Crawford discovered that his intake vents required different settings based on wind direction, outside temperature, and interior activities. Cooking meals or drying wet clothing demanded increased ventilation that could be reduced during sleeping hours when moisture production dropped significantly. The most sophisticated element was a heat recovery component that Crawford developed through trial and refinement. He constructed a series of internal baffles that forced outgoing warm air to pass close to incoming cold air, transferring heat between the air streams without allowing them to mix. This primitive heat exchanger recovered approximately 30% of the thermal energy that would otherwise be lost through ventilation, maintaining his cabin's efficiency while solving the moisture problem. By December of 1861, Crawford's ventilation system was maintaining interior humidity levels between 40 and 50%, even during extended periods of sealed cabin conditions. His hygrometer readings showed consistent moisture control that prevented condensation, while his thermometer confirmed that interior temperatures remained stable despite the controlled air exchange. The Kowalski family, struggling through their third winter in a cabin plagued by constant dampness and occasional ice formation on interior walls, observed Crawford's moisture-free environment with growing interest. Thomas Brennan, whose standard cabin developed serious mold problems during the wet spring of 1862, finally acknowledged that Crawford's systematic approach might have merit beyond simple eccentricity. Crawford's integrated systems now addressed every major thermal challenge that frontier construction typically accepted as unavoidable. His low ceiling trapped heat in the living space. His earth-coupled foundation eliminated cold floors. His insulated walls prevented heat loss through the building envelope, and his ventilation system controlled moisture without sacrificing thermal efficiency. The cabin had evolved into something unprecedented on the American frontier, a structure that maintained superior comfort using minimal fuel while creating healthy interior conditions regardless of outside weather. Crawford had proven that systematic application of thermal principles could overcome the limitations that territorial construction standards accepted as facts of frontier life. The approaching winter of 1862 would test his complete system under the most severe conditions Wyoming Territory could deliver. The test of Crawford's integrated thermal system came during the winter of 1862 to 1863, when Wyoming Territory experienced the most severe cold snap in recorded frontier history. Beginning on December 18th, temperatures dropped to 37 degrees below zero and remained below -20 for 17 consecutive days. This extended Arctic outbreak, driven by a persistent high-pressure system centered over the Canadian Rockies, created survival conditions that pushed every heating system on the frontier beyond its normal operational limits. Crawford had prepared for this trial by establishing systematic data collection protocols that would provide quantifiable evidence of his cabin's performance. Throughout the autumn, he had calibrated his mercury thermometer against instruments at Fort Laramie and created a daily measurement routine that tracked interior and exterior temperatures at 4-hour intervals. He maintained detailed fuel consumption records, weighing each piece of firewood before burning and calculating heat output per cord of split pine. On December 20th, when the temperature reached -32 degrees and stayed there for 48 hours, Crawford's integrated systems faced their ultimate test. His thermometer readings revealed the precise advantages his modifications provided under extreme conditions. While outside air registered 32 degrees below zero, his cabin's interior maintained a steady 72 degrees Fahrenheit, with his fireplace consuming approximately 12 pounds of split pine every 4 hours. Thomas Brennan's identical-sized cabin, built using standard territorial construction methods, required 26 pounds of firewood during the same 4-hour period to maintain an interior temperature of 58 degrees. The Kowalski family, burning furniture and fence posts to supplement their dwindling wood supply, achieved interior temperatures that peaked at 52 degrees before dropping toward freezing as their fuel ran out. Crawford's fuel efficiency advantage became more pronounced as the cold snap continued. His earth-coupled foundation prevented the ground-level heat loss that plagued elevated cabins, maintaining floor temperatures of 54 degrees even when his fire burned low during sleeping hours. His insulated wall system eliminated the thermal bridging that made standard log construction act like a massive heat sink, while his controlled ventilation system maintained healthy air quality without the dramatic heat loss that uncontrolled air leaks created in conventional cabins. The most significant advantage appeared in Crawford's ability to maintain consistent temperatures using predictable fuel consumption. While his neighbors faced the constant uncertainty of rapidly diminishing wood supplies and increasingly cold interiors, Crawford's systematic approach allowed him to calculate exactly how much firewood he needed for any given outside temperature. This predictability meant he could manage his fuel reserves with confidence, avoiding the panic that drove other settlers to burn irreplaceable possessions. By December 28th, when the cold snap had persisted for 10 days, Crawford's neighbors began seeking his advice. The Kowalski family, facing the possibility of freezing to death in their standard cabin, asked to shelter in Crawford's modified structure. Brennan, who had initially mocked the low ceiling design, appeared at Crawford's door requesting technical information about foundation modifications that might save his freezing family. Crawford's response revealed the systematic thinking that had guided his entire approach. Rather than simply offering temporary shelter, he provided his neighbors with specific technical information they could use to improve their own cabins. He shared his thermometer readings, fuel consumption calculations, and detailed explanations of each thermal principle his modifications employed. Most importantly, he demonstrated that his methods could be adapted to existing structures without complete reconstruction. The immediate impact was measurable and dramatic. Brennan spent 3 days lowering his cabin's ceiling from 8 feet to 6 feet 6 inches, using techniques Crawford demonstrated. Within a week, Brennan's fuel consumption had dropped by 20%, while his interior temperatures increased by an average of 8 degrees. The Kowalski family, working with materials Crawford provided, added moss and clay insulation to their interior walls and achieved a 12-degree temperature increase with 30% less firewood. Word of Crawford's thermal efficiency spread throughout the territory with remarkable speed. The territorial land agent, conducting emergency welfare checks during the cold snap, documented the temperature and fuel consumption differences between Crawford's modified cabin and standard frontier construction. His official report to territorial headquarters described Crawford's methods as representing a fundamental advance in frontier building techniques that could prevent cold weather fatalities across Wyoming territory. By February of 1863, settlers throughout the region were implementing Crawford's modifications. The postmaster at Fort Laramie reported unusual demand for technical information about cabin modification techniques. Trading posts began stocking bog moss and clay materials as settlers recognized their value for thermal improvement projects. Crawford's success attracted attention beyond Wyoming territory. Military engineers from Fort Collins traveled north to examine his thermal systems and evaluate their potential application to military construction in cold climates. Their detailed measurements confirmed Crawford's performance claims and recommended adopting his techniques for frontier military installations throughout the Rocky Mountain region. The broader implications of Crawford's work became apparent during the construction season of 1863. New settlers arriving in Wyoming territory increasingly chose to build cabins using Crawford's thermal principles rather than standard territorial methods. Low-ceiling construction became common rather than exceptional, and foundation systems that utilized earth coupling for thermal stability replaced elevated designs throughout the region. Crawford documented this transformation through systematic observation of construction projects within a 20-mile radius of his homestead. During 1863 and 1864, approximately 60% of new cabins incorporated ceiling heights below 7 feet, while 30% used some form of earth-coupled foundation design. Wall insulation systems, though requiring more specialized knowledge and materials, appeared in 15% of new construction projects. The long-term vindication of Crawford's approach appeared in survival statistics compiled by territorial authorities. During the severe winter of 1862 to 1863, no settlers using Crawford's thermal modifications experienced cold weather fatalities or serious frostbite incidents. Standard frontier cabins in the same region recorded 12 deaths directly attributable to inadequate heating and cold exposure. By 1865, Crawford's thermal principles had evolved from individual innovations into accepted frontier building practice. The Wyoming Territorial Building Code, adopted that year, recommended ceiling heights between 6 and 7 feet for new residential construction and specified foundation designs that incorporated thermal stability principles. Wall insulation requirements became standard for buildings constructed above 4,000 feet elevation. Crawford's legacy extended beyond immediate practical applications into systematic thinking about frontier challenges. His approach demonstrated that careful observation, measurement, and systematic testing could overcome accepted limitations that previous generations had considered inevitable facts of frontier life. His method of integrating multiple thermal systems into coordinated solutions became a model for addressing complex technical challenges throughout the developing West. The transformation of Wyoming Territory's building practices represented more than simple technical improvement. Crawford had proven that systematic application of scientific principles, combined with respect for traditional knowledge from multiple cultures, could create solutions that surpassed both conventional wisdom and individual innovation. His cabin became a demonstration that frontier survival could advance through systematic engineering rather than mere endurance.